I have my local recording going great. So welcome. Yeah, yet another Friday, yet another lab. Actually, I have one more lab lecture. If you look at the schedule, next Friday we're going to do another lab lecture for all the remaining labs. And then from this point on, we're just going to cover theory both Monday and Friday. Today we're going to do lab 7. We've extended the deadline for lab 5+6 until Sunday. I pushed the code for lab 7 into the skeleton, but I haven't merged it with master yet. I have it on my calendar to do this on Sunday after the deadline for lab 5 and 6, just to avoid any kind of confusion to people still pulling things from Git. So if you want the code for lab 7, it's in the repository, just not in the master branch. So what we're going to do today. So we're going to talk about the labs again, just to sort of give a better idea of what are we doing, what is the end-to-end goal. We're almost there. From the theory perspective, we're going to talk a little bit about non-determinism. Just because it's a concept that sort of is important, we've seen it before in case of non-deterministic automata. We'll talk a little bit about it here. Then we're going to cover a number of programming concepts. This is a concept which are important for this lab. In particular, we're going to look at the visitor design pattern, which is a new design pattern we haven't seen yet. The design pattern you have to use in the lab, and so you better understand what it is so that you can understand the code given to you and how to use it. And then finally, the lab itself is about producing circuit from our F programs. And as part of it, we'll need to do common sub-expression elimination, so that our circuit does not recompute the same sub-expression twice. So that's a compiler part of that lab. All right, so what are we doing in the lab? So what's our big picture? This is what we're trying to construct overall. We're going to start with a language that says VHDL in the picture, but really it's a variant of it. So I prefer to refer to it as just V, just like other languages, we have a single letter name. And so what we want to do is we want to be able to go from this guy into two directions. One, we want to construct a circuit out of it. In our case, the circuit will just be pictorial representations of a circuit. This is actually what we're doing in lab 7, this guy, technology mapper. And then the other end of it will be that we want to generate a simulator. That is, we want to take our VHDL circuit and turn it into something that's executable. And as it executes, the output, it's going to output a waveform, which is our W language, which we then want to visualize and see as a binary waveform. So this is our overall structure. And you can see which labs we already done and which ones are yet to do. So this one we've done, right? So we've done parsing and simplification of F. These parts we've done. And the ones that are coming is the technology mapper is today. And then we have a simulator generator to do and preprocessing at the V level of starting from a more complicated V specification, simplifying it to a simpler one, and then eventually synthesizing a combinational circuit out of it. Okay, so lab 7 is today, and 3 more labs are remaining. This is, again, just to give you an expectation of what we're trying to do. We want to go from a circuit like this. So in this particular case, you see this is a full adder, right? So we have a specification of a full adder with its inputs and outputs, and then we have its implementation in terms of the gates. And from there, we want to be able to construct, first of all, just the actual circuit. So this is what the input is to lab 7 will be. It's this kind of F programs, which are, a simplified version of this, where we just get the circuit itself. And then in lab 7, what we want to do is we want to generate the circuit, which in our case will be a picture like this, a picture of gates, where we have our inputs here, here, and here we have our output, and then this part, the gate representing the formula. And you see, of course, here, if you look at any gate, every gate computes some kind of function, some kind of sub-expression, and we don't want the same gate to be computed more than once. So here, for example, we'll see that the output of this gate is used as an input to this one, as an input to this one, as an input to this one. Whereas in the original formula, we would have this expression appearing inside the formula multiple times. Right, so if we go here, we'll see that there's common sub-expressions all over the place. For example, this not A and B here, and not A and B here, and not A and B here, right? Which, of course, we don't want to, when we build a circuit, we don't want to build a circuit to compute the sub-expression more than a single time. All right. So that's a lab expectation. Let's see if there's any questions. Probably there aren't. But let me just pause for a second. Okay. So the next concept is a theory concept, and it's really just a short remark about the nature of non-determinism in general in computer science. So we've seen a non-determinism in a sense, in the case of non-deterministic automata, where an automata non-deterministically picks what to do. We often see non-determinism when we talk about correctness of a code, where we want to say the code is correct against an arbitrary input that is chosen non-deterministically. And it's good to sort of understand some of the differences and have a good terminology so that we can talk about those things. So a non-determinism by itself simply means that a choice has to be made, and a choice is made, one thing is selected, and this choice is not determined by anything. It's in some sense arbitrary. The important thing to remember is that non-determinism is not the same as randomness. Randomness is an arbitrary choice that follows a certain probability distribution, whereas non-determinism is the choice that's just arbitrary and it doesn't follow any distribution at all. And when we talk about non-determinism, depending on our context, we can talk about non-determinism that is somehow positive, somehow helps us, non-determinism that's somehow adversarial, somehow hurts us, or just non-determinism as a form of abstraction where we're saying, well, actually, probably it's not really non-deterministic. The choice is probably not arbitrary, but we just pretend that it is. And so for this, we have the three terminology. We say that a non-determinism is angelic if the non-determinism is somehow helpful to us. So for example, when we take a non-deterministic automaton, we say an automaton accepts a string, it fulfills its action, as long as there is some oracle that can go, and every time where an automaton has to make a choice, the oracle helps an automaton make a choice in such a way that it ends up in an accepting state. So if an automaton can make a choice to get to an accepting state, then it accepts. That's an angelic non-determinism. We use this kind of non-determinism when we say specifying an algorithm, and we want to at least understand whether we are on the right track. So we may have a partially specified algorithm, and we say, well, we don't know how to implement this particular component, but if there is a good oracle that can, then the rest of the algorithm works. Sometimes that oracle is something that we can then actually implement. So with a non-deterministic finite automaton, we can convert it to a deterministic finite automaton, essentially implementing that oracle. And sometimes it may be that we can't implement that oracle. So for example, if we need to solve an unsolvable problem in order to make the right decision, well, then we can't actually turn that non-deterministic algorithm into a deterministic one. But we may, for example, turn it into a probabilistic one, where we'll make this choice using some randomness. Now, The second kind of non-determinism is the one that happens when we think about testing or verification of our programs, something like that, where the non-determinism is adversarial, and so we call it demonic. So this is a antonym of angelic. A demonic non-determinism, it means that every time we look at the non-deterministic choice, we always assume the worst possible situation. So if, for example, I want to test my program against certain inputs, I will assume that whoever is creating the inputs, the inputs are created non-deterministically and demonically. The question I will have, is there a way to feed inputs to my program so that it doesn't behave as expected? For example, so it crashes, produces the wrong output, and so on. So this is demonic non-determinism. And again, the reason we have it, it's a form of abstraction that we represent something that, sort of happening that we don't really know how it's actually resolved. And if we can show that our program is correct against a demonic non-determinism, that means that it's correct against any input. And if it's not correct against demonic non-determinism, it doesn't mean that it can actually be, for example, attacked, because again, the oracle is non-deterministic, so it doesn't necessarily mean it can be implemented. But it's a good, strong way to abstract adversaries. And finally, we have this third kind of non-determinism, where we really can't say that it's positive or negative in particular. It's really just that we want to abstract something. And this is most commonly happens when we want to express what the program is doing, but we don't really want to give all of the details of how it's actually done. In which case we pretend that the way the program behaves is indeterminate. That is, we don't know what the output is. We don't specify any probability distribution, so it's not random. And we don't really have any particular goal in mind. We're not saying that, well, it's non-deterministic and it solves the problem, so it's not angelic. And it's not that it's non-deterministic and there's somebody malicious tries to hurt us, so it's not demonic. It's just something unknown happens, and we want to indicate that. Of course, so whenever we think that our program has non-determinism, the important thing to realize is that that makes testing difficult, because then on the same input, the program may produce more than one output. And if it's non-deterministic, then both outputs are correct. And so when testing gets harder, because writing in Oracle that checks that the result is as expected is harder. Okay, so why do we care about non-determinism? I mean, this is really the biggest thing. That it's a concept that appears in lots of places. It's good to know it. It's good to know the terminology. We see it through various parts like non-deterministic automata. So good to know about it. It appears in all kind of places. You have heard about NP-complete, where N actually stands for non-deterministic, and that corresponds to angelic non-determinism. And it's a powerful abstraction that a good thing to have to keep thinking about how I can break the problem into thinking about what I can do, and if I have an oracle and it's a positive, negative, or an arbitrary oracle. Now, this is an example of where we have this arbitrary non-determinism, which is neither positive nor negative, where we really use it just as a way to abstract the details. Okay. So, for example, whenever we using a hash structure, where exactly an object gets stored in this data structure depends on a lot of very specific things. So an object will have a hash code, and the hash code may depend on where the object was allocated in memory. And then it depends on the size of the hash table, or how many entries we have right now. And that depends on how much memory we have in the machine, because we won't make a table too big. It depends on how many objects are already stored. It depends on order in which objects were stored and removed, and whether there were any collisions or not. And of course, if you have any particular piece of code, and I insert an object into hashcode, I could figure out exactly where the object will go. Except that it depends on all of those things. And so a good way to abstract it away is to say, I'm just going to pretend that the object will be somewhere in a hash table. It will be in some place in there, somewhere inside that array. And so I'll just assume that the location that where this object is placed is non-deterministic. In practice, it's not non-deterministic because we don't have any algorithms that work non-deterministically. But unless I want to consider all of those details, it appears non-deterministically to me. Another big source of non-determinism, at least in this kind of thinking, is concurrency. Not something that we're dealing with in this class, but something that I'm sure you all are familiar with. Whenever we have a multi-threaded program that executes multiple threads, the execution is interleaving of those threads, and the order in which the execution happen, we like to pretend that it's non-deterministic. Again, in an actual machine with an actual scheduler and an actual execution, it's very deterministic. If you run a program, a multi-threaded program, in exactly the same environment twice, you're going to get exactly the same sequence of actions. The problem is that running it in exactly the same environment twice is very hard because it depends on the scheduler, what else is happening in the operating system, and all of these other factors, which are very, very hard to replicate. And so instead of thinking about this as a deterministic computation, we pretend that it's non-deterministic. It's neither positive nor negative. We're not thinking of, say, a scheduler as helping us. We're not thinking of a scheduler as hurting us. We're just pretending that the scheduler non-deterministically picks an instruction to execute and execute that instruction. Okay. So continuing with this, we're going to look at an iteration order of objects in a data structure. And so we'll see, again, this non-determinism appearing and a way to deal with this. So let's see if we can get an answer to this question. So I have an array list right here. This is this. I insert 3 elements, 3, 1, 2, and then I print the list. So what will be printed? I'm going to wait for somebody to answer on CampusWire just to see that we are in sync. Okay. So what's going to get printed is 3, 1, 2. Right? So the order in which the output comes corresponds to the order in which the elements are inserted. Right? So we have insertion order, order in which the elements are inserted, and that's the order in which they are printed. Now, what if I'm going to go and I'm going to change my data structure from an array list to a tree set? And again, I insert 3, 1, and 2. And then I print this thing. What will be printed? Again, I'm waiting for somebody to suggest. All right. And of course, the output here will be 1, 2, 3. Right? And why? Well, because tree set keeps its element in what is called a natural order. So it uses a compare to compare the elements between themselves, whatever that happens to be. In numbers, it's 1 less than 2 less than 3. And when we print, we get the elements produced in that order. So we have insertion order, the order in which we insert elements into a collection. And then we have a natural order, which is an order in which the elements are ordered naturally according to their comparative function. And an array list, the order in which we can traverse the elements is exactly the same as the insertion order. So we get to see which element was inserted first. In tree set, the insertion order is not preserved, but the elements are ordered in a natural order. So at the very least, we know whenever we do this print, we can immediately predict just from this code what will be the output. So it's very deterministic. It follows a natural order. Okay. Now let's go further and we're going to replace the data structure by a hash set. So what is going to get printed in this way? So somebody says the output will be unordered, right? But that's, what does that mean? So for example, could the output be 1, 2, 3? Is that a possible output? Sorry, it keeps disappearing. I can't. I don't know how to keep it from disappearing, but I like the presentation mode for showing the slides. All right, so 1, 2, 3 is possible. This is ordered. And also 3, 2, 1 is possible. And maybe 2, 3, 1 is possible. Right? But are they actually possible? Can you actually, if you write this program in, say, Java 11 and you run it, can you get all the different orders that we saw? Right? It's a very hard question. We don't know. It very much depends on how this data structure is implemented and how collisions are handled and all of those things. So it's not necessarily that the order can be arbitrary. It is something, and it, for example, could differ from Java 8 to Java 11, or from one version to another, or from one implementation like OpenJDK and Oracle JDK could have a different output. So because it's really complicated to figure out what's actually happened, so we'll say that the output is non-deterministic. And this is why we were talking about non-determinism. So one way to think about it is to say, well, the output, it's not that it's unordered. That's a very strong statement that says it will not be ordered. It's rather that the order is indeterminate. And not that in any implementation it's not determined. It's really, we want to indicate that as programmers, we shouldn't rely on any particular order. We should pretend as though it is chosen arbitrarily, as some non-deterministic oracle picks an order in which to produce this element. Yeah. So it's an arbitrary non-deterministic choice of those things. And it doesn't have to be, so it's not probabilistic choice. It doesn't have to be that, all of those things are equally likely. And it doesn't have to be that in any implementation, an output is, changes from run to run. It would be very, very fixed. It's just our abstraction, our mental simplification, where we say, well, we're just not going to know what the order is. Okay, so we know what a set is. Okay, so this was iteration order. Okay, so we're going to get back to it if we care about insertion order still. So the next thing is we need to talk a little bit about object identity. So we have a notion of a set, which we all know about, right? So it's an unordered collection of distinct objects. So unordered is easy, meaning we don't put any order. Distinct is hard. Distinct means different, and the different notion of what different is. So this is what we need to really understand, even so we've seen this before, but in this particular lab, this is really important. So what does it mean for objects to be different? There are different ways to do it. In Java, there's two main ones, which are these two. This is two different ways to compare an object. So this way, we say two objects are different if they occupy a different space in memory. So we don't care what the objects mean logically or semantically. We don't care about what they represent. All we care about is where they're allocated in computer memory. Are they exactly the same object and exactly the same address, or they're different? So this refers to the physical memory address, and this is often referred to as identity. So we'll say two objects are equal if this equality means we compare identity of objects. The second way to compare objects is through equals method. Right? So equals method just looks at x and y, and it returns true if these two things represent the same semantic object. That is, from the perspective of the code of the program, some part of the code, there is no difference between x and y. They functionally behave the same, and they should be treated as meaning exactly the same thing. Doesn't mean that they're the same object. It just means that actually, if you look inside, they kind of look the same. Most of the Java collection data structures either use this. If they do, they'll have identity in their name, or this. And this is the default one. So if you just use a data structure like a hash set, for example, then you know it uses equals, this kind of equals for comparison. But we also have other forms. We have isomorphic, and we have equivalent, for example. Right? And so we need to know whenever we're building a data structure, if we're using a standard data structure, then we know that it's going to be using equal, so identity. And if we want to rely on some other notions, we have to somehow bring them to the data structure, either by programming around it or by defining special compare methods. All right, so let's look again at the example of a hash set. So say we have the following hash set, and I'm inserting 3 elements, y, x, x, and then I print this hash set. I know that the order will be non-deterministic, so it's either going to be y first or x first. The question is, am I going to have 3 elements printed or 2 elements? 3 printed or 2 printed? To answer this question, so this is just a hash set, right? So we didn't say anything about what does it mean for elements to be equal, which means the equals method is going to be used. And so it depends on the equals method of var expression, which based on the name. So we expect the output to have only 2 things. Right? So this is exactly what we should get, either xy or yx. That's the 2 choices. Now, we could actually want to have a set, but also remember an order in which the elements were entered into it. That's often a convenient thing, because you may want to say that, the first thing that I entered into the set, I want to remember that it was first, and the second, I want to remember that it is second. For that, we have this data structure called linked hash set. Hold on, link hash set, okay. And so this one extends the hash set with also remembering the order in which elements are inserted. Right? And you can imagine that one way to implement it is that under the hood, what it does is that it represents, it has a hash set to keep the elements in unordered but unique way. And then on the side, it has a linked list or something like this to keep track of the order in which elements were actually were entered into this collection. So with a link hash set, the output will just be yx. It will only have 2 elements because this is a set, and in the order in which they were inserted. And again, link hash set, because it has nothing, there's no identity in its name, it means that it uses the normal equality equals method. Now, finally, our other alternative is to have to use an identity hash set, this guy. And an identity hash set resolves equality using object identity, so the double equals. So in this case, what we expected to be printed is actually 3 elements, y, x, and x, but the order is now arbitrarily, right? Because this is a normal hash set, so it doesn't preserve an order, it's not linked. but it uses identity, object identity instead of equality. So that's what we're going to get. So and here, so what the slide shows is that the order in which x's are printed will be arbitrary. And just to indicate, since both of them are called x's, we don't know which one is which. There's this 1 and 2 added in here. They're not part of the name. They're just here to indicate that x2 is the second x that was added, and x1 is the first. So if we take these objects and we print their object hash code, they're just going to be different numbers because they're in the different places in memory. Okay. Now, all of this will be important for the slab, so you're going to have to worry about separating between object identity, which is maybe a particular part for which you have constructed a circuit, versus an object equality, which will be an expression which is equal to an expression that you've already constructed. And so one way to manage this is to use this data structures. You'll see hopefully which data structure will be useful where you can simplify your code, if, for example, using an identity hash set as opposed to a normal hash set. Okay, so there's a question that maybe I've confused some of you. So there is a question on chat that says something use.equals for object identity. So maybe we need to go back. So we have identity hash set. So to check the two objects are equal, it uses object identity, which is the double equals. The other data structures, the not identity one, they use equality for object equality. Right? I guess, okay, so the issue here is with the terminology. Let's see. So an object identity here, it's going to be, so, right, okay. So in the slide, we use the term object identity to mean when the two objects are equal. And we say we can identify two objects by double equal, by their identity in memory, by their equals, by their equality, or by other means. Okay. Now, outside of the slide, it's a common way to say that we can compare two objects either by their identity, which is double equals their address, or by their equality, which is equals. And so that's why there's a little bit disconnect between the names in the standard Java collections and the terminology in the slides. Okay? So identity here really means object identity, which means double equal. Yeah, this both equality and identity of objects is always very, very confusing, and the terminology does not make it easier. Because there's many ways in which things can be equal and also different, and you have to be careful about which one you want. Okay. So I'm going to pause for a second here because we're going to move to a next concept, and that's perhaps going to be the most complicated concept of this lecture. Let me do a short poll. Not sure how this will work on CampusWire, but I just want to know how many people have heard of a visitor design pattern. So if you have or you haven't, just say something on the chat. So I see mostly no. 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 All right. All right. So then it's gonna be then maybe interesting for you, and definitely very valuable. So first of all, we talked a bit about design patterns before. So design patterns is just a way to structure code to achieve a certain function. The reason why we like them is twofold. One, it gives us a template solution. So as you're designing something and you know some characteristics of what you're designing, you can pick from design patterns rather than trying to come up everything from scratch. That's one. Second reason why we like design patterns is because they communicate to others what is our intention. And so if I look at somebody else's code and they were using design patterns and they actually use proper names for those design patterns, then I can immediately spot parts of their code. And without going into too many details, I already understand how the code is structured and roughly what it's maybe trying to do. So the sort of big design pattern of today is a visitor design pattern. And it's an alternative to an interpreter design pattern, which is something that we saw before with the simplifier. So we're going to talk a little bit about the interpreter design pattern, and then the visitor design pattern, and why, what's the alternative, why is it good, why is it bad, and look a bit at how it's actually done. The difficulty with the visitor design pattern is that it's based very much on polymorphism. So you take your code, you put it into different pieces in your program, and because of the polymorphic call resolutions, you expect the right piece of code to be executed at the right point in time. And so that's what makes it a little bit complicated to understand initially, because there are multiple pieces, and you just have to make sure that you understand how all the pieces connect. Once you do, you can forget the actual details of how they connect and just use the pattern. I find that's very similar to understanding recursion. When you start understanding recursion, it's very complicated. You have to keep track of how it's actually implemented, how it's actually working, what's going on in every step. But after a while, once you get used to it, you just write recursive code without thinking too much how exactly it's executed, but just think about how it fits the algorithm that you implemented. And so expect the same here. Like drawing lots of object diagrams, looking over simple examples will go a long way in improving your understanding. And once you do, then you'll just be looking at and saying, oh, visitor pattern, easy. I just need to know where to put the right code here and not worry about how eventually this code will get executed. I just need to worry when it gets executed. Okay. So first, interpreter. This is what we used in a simplifier before. Not to be confused with interpreter in this sense. So there's an interpreter as in something that interprets a program, executes it while compiling in a sense. We're talking about interpreter in a sense of a design pattern. And this is a useful design pattern for lots of things, and in particular when we're writing program evaluators, and in particular whenever we already have a composite design pattern. And remember, a composite design pattern was a way to represent a hierarchy of elements, kind of like our expressions, where we structure the code that we have a base superclass-like expression that represents a collection of other things, and then leaf classes like AND expression, NOT expression, and so on. So this is our composite design pattern class diagram for expressions. So we have our composite, and then we have our leaf things in here, the NOT and the NOR. Okay. And the idea of an interpreter pattern is that you break down whatever you want to implement into how it's implemented, but by each individual element of your hierarchy. And you simply add a method to implement it everywhere in a hierarchy. So for example, what we'd like to do is to simplify an expression. And so we say, okay, then every part of this expression hierarchy knows how to simplify itself. Right? And so we add the code for simplifying not in one place, but rather we sprinkle it through the hierarchy. And for every element in our hierarchy, we add its own simplify method. Sometimes we use our inheritance to simplify our coding, so we don't have a simplify method in here because we happen to just inherit it from here. But in general, any every member, or every leaf of the hierarchy should have an implementation of simplify, and the composite, the one at the top, should require that simplify is implemented. And if you think about how simplification works, that's the interpreter design pattern. Okay. So this is good, but let's think about using this pattern for everything else. So we've done the simplifier, right? And in order to write the simplifier, we had to go and add code for every class, for every leaf in our expression hierarchy. Again, sometimes we implement code in a superclass and it's inherited, but essentially the code is sprinkled through all of our AST classes. Then, in addition to simplifying, we want to do pretty printing. Again, if we use the same design pattern, we put code in every expression. If we want to convert to gates, which is the technology mapper, well, then again, we would have to say, how do we convert an AND expression, an OR expression, of our expression? And, we go and we add a function everywhere. Okay? And you'll see that quickly, this gets a little bit out of control. Our classes, the classes in our hierarchy, these guys, they start adding more and more functions. So every time we want to add yet another kind of operation on them, if it's something that every element in a hierarchy is doing somewhat differently, if we're using an interpreter pattern, we go and for every class representing an expression, we add an extra method. And that's, of course, not very convenient from the perspective of code maintenance. So if we have, for example, different things that we want to do that maybe are not always shipped together, some things that are becoming old, some things that are only done in a certain time or only part of some product and not part of every product, if we keep adding everything inside every class in our hierarchy, it's very hard for us to separate these concerns and say, oh, I have this functionality and it's here, and I want to edit or not edit. And this is where the visitor design pattern comes. It's a different way to organize your code. So you want to organize your code in such a way that, on one hand, you still have this part of the structure, that for every kind of element you have its own function that knows that it's attached to this kind of element. So this is simplify of a binary expression, simplify of a constant expression, simplify of a var expression. So that you want to keep, but you would like to take all of those functions and move them together into a separate class so that they don't clutter your abstract syntax tree hierarchy, so that they don't clutter your composite pattern. Now, of course, that's not going to be too easy because we kind of have a thing that wants to be together and we want to split it apart, but still feel like it is together. And this is where polymorphism comes to the rescue. Okay. So this is what we would like to have. We would like to structure our code in this way, where we have whatever we functionality we want as a separate class. So maybe here it will be called simplifier. And it has all of the simplify method for all expressions. And so if we want, we can take our code without the simplifier, and we have code without simplifier, and simplifier doesn't clutter our code. Or we add a simplifier and we have a code with simplifier. Right? As opposed to in the interpreter design pattern where everything is kind of built in right away. Right? So all the code is scattered in the interpreter pattern and attached to all of our to all of the individual members of the hierarchy. So the traditional way to name things is to use the following naming convention. So now this is where sort of using common names is helpful, because now after this, once you see those names, you'll know exactly what is meant. But the choice for names is arbitrary. They could have been named something else. So the way we're going to structure our code is in the following way. In a simplifier, we're going to say that it's going to have a method called visit for every kind of member in our hierarchy. I have a visit for an AND expression, visit for an OR expression, visit for a NOT, visit for a constant, and visit for a var. And the code for the visit method will be the code that I want to do at this particular class. So for example, visit NOT expression in a simplifier will do the simplifications that are done at the NOT expression. And this code will just live together in one class. Now, in order to connect this class to the rest, I'm gonna add an accept method in every class in my hierarchy. And what the accept method will do, it will take a visitor as an argument, and it will call an appropriate visit method in the visitor. Okay. So I'll have, if I have a visitor v and I have an expression e, I will have code like this. And through polymorphism, it will resolve into v dot visit. And this is whatever is the type of e. And e will be put as an argument. And once I have this, once I combine the things together, what I'm gonna get is that I'm able to take everything that I need and every functionality that I have for each individual kind of function I want will now be in its own class. The simplifier is in a simplifier class that extends the visitor. Pretty printer is in pretty printer class. Technology mapper is in a technology mapper class. And now it's easier for me to combine all of those things and manage them. So at this point, we really need to look at an example. So we're going to look at a bunch of code. So let me, so we did accept and visit. Let's go to the code. Okay, so I need to switch to my VS Code and switch here to my editor. Okay, let me know if this is too small on your screens. I can zoom in a bit if necessary. So we're going to look at the implementation of a visitor for our AST. So the visitor itself, the base class, is expert visitor. You don't see my mouse, but hopefully you see what things are highlighted. And if we look at an expression visitor, all that it is, it's an abstract class, and it has abstract methods for visiting each individual expression. So it says visit constant, visit variable, visit negation, visit AND, visit OR, and so on and so on. Okay? This is all the different things we can visit. The way it is connected to the abstract syntax tree is that in the abstract syntax tree, for every kind of an expression, so here I'm at the AND expression, we have a method accept. The method accept takes a visitor as an argument. And what it's doing, it's calling the appropriate visit method on the visitor. Okay? Now, so what this lets us do is that if I have some expression E, and I don't know what is the type of E, I don't know whether it's an AND or an OR or whatever, and I call accept on E. So I have code that's written e.accept. Well, through polymorphism, the compiler will figure out which accept gets called. It's an accept of whatever class corresponds to E. So for example, if I call accept on an AND expression, even if I don't know that it's an AND expression, this gets called with my visitor passed as an argument. And this code, because it's code inside AND, it knows that it's an AND call, and so it will call vvisit AND on this expression. So let me add just a little example here. So what that means is that assume E is an expression of type AND expression. Okay? Then the call e.accept v via polymorphism will resolve in v dot visit and e. Okay. And again, to understand this, the easiest thing is to try a small program and draw an object diagram and see how things look like. So we have e.accept. So I need to know where e points to, what in my object diagram, what e is. If it's an AND expression, then accept is this function. And if this accept function is called, then it takes v as an argument and it calls an appropriate visit method on e, on v. So a call like this, e accept v, where I don't know what e is, I don't know what the type of e is, I just know that v is a visitor, ends up being exactly the same as on a visitor to call visit and give e as an argument. And this way, v knows that, well, e is an and only the code for and will run. Now, there's a question in the chat and say, why can't we make an AND expression also extend the visitor class? And that's not the right question to ask. So we're trying to separate, we're trying to write code that's in an interpreter pattern would be inside an AND expression. But instead, we want to structure a code so that code that's related to a functionality, like simplification, 3D printing, or technology mapping, is in one class. So we have a hierarchy, the AND expressions, OR expressions, all of those things. And we would like to write code that does something for each member of that hierarchy. And for that, we create a visitor. A visitor defines all of the members of the hierarchy, all of the places where we can put the code. And in the hierarchy, we just need to implement the accept method to bind a visitor to that member of the hierarchy. There's another question whether the visitor design pattern is possible and common in C and C++. So in C, not so much, because C is not an object-oriented language, so there's no polymorphism. And in C++, yep, very much so. And actually, in almost any language that has object-oriented facilities, a visitor design pattern would be used. And again, it's a sort of a common way if you have a hierarchy and you would like to then do something that works with every member of the hierarchy, a visitor pattern is more or less what you'd always use. So there's a question whether we can use a function overloading instead of this. And the answer is no, because if we look at this example where we have here, so if instead, function overloading will not work because I may not know what the type of E is. So I can have E could be an expression, and then I have expression. Well, so let's see. Maybe I would want to say, yeah. So I have an expression visitor E, and then I would say something like vvisit E, and I would expect an appropriate visit method to be called. But it won't, because E is only known to be an expression. At runtime, dynamically, E could be an AND expression or an OR expression. But at this point, when I compile, I don't know. So function overloading will either say, I don't know what E is and I don't have an appropriate visit method for it, or it will have to say, I have to call visit expression, and then visit expression has to figure out how to forward it somewhere instead. All right. So let's then go a bit further with this, and let's look. So we looked at that. Okay, so we now have to remember that every member of our hierarchy has an accept, And whenever we call accept, it's essentially that we're calling the right method in a visitor, and we're using polymorphism to figure out which way to call. Yeah, and so there's a question. So function overloading takes place at compile time, and polymorphism takes at runtime. Yep, that's exactly right. Polymorphism is a runtime feature, whereas the function overloading is a compile time feature. Okay, so let's go back to our expression visitor. So this is how we're visiting different expressions. Now, this particular visitor, the one that we're using, it also adds an ability to traverse expressions. A visitor is just saying, what to do at an end or and so on, but not how to navigate them. So our visitor also has a convenient methods to traverse expressions. So there's a traverse expression method, and all that it does, it just figures out which type an expression is and calls an appropriate traverse method. And then if all of those fails, right, then it just says, tell E to accept the current visitor, right? So if it's not an n-ary, not a binary, not a unary, so it means that it is a leaf expression, then to traverse a leaf expression is simply call accept on E, and this will, of course, will end up being a call to visit in here, the one of the visit at the top, depending on the type of E. Now we leave traverse n-ary, binary, and unary expression abstract. And to traverse a program, we traverse all of every assignment in the program and combine this with the result and return the result. So now with this, we can extend it further. And the extension we have is a post-order expression visitor. And the post-order expression visitor extends the expression visitor by implementing some of these traverse methods so that we have a post-order exploration of the AST. Post-order means that we first traverse the children and then we traverse the parent. So again, if we look at the code here, so what does it mean to traverse an unary expression? Well, we're going to look at its expression field. We're going to call recursively traverse expression to traverse that field. The traverse expression here will return, because we're assuming that we're visiting and also doing a rewrite. So it will return the new rewritten expression if we did any rewrite, or the same expression if we didn't. We're going to check if the new expression that's returned is actually different. If it is, then we're going to update. We're going to recreate our expression u to be the new expression. So same operator at the top, but a different child. And otherwise, we just keep u as is. And now finally, we call a visit method on the u itself, right? But we don't know what the exact type of u is. So to call the appropriate visit method, we call u.accept. And through polymorphism, that results to a call to a visit method in us, depending on the type of u. Okay. Same for binary. We just need to go left and right. Same for n-ary, except that we have to go to every child and then remember whether any of the children have changed. And that's it. Okay, so that was a bit much. So now finally, we get to reap the benefits. So let's say we look at this thing. So what we'd like to implement is a piece of code that goes through a formula and extracts all sub-expressions of that formula. So now this is where the visitor pattern really shines. So what we really need to think about is what do we want to do? How do we collect all the different subformulas? So for every member of our hierarchy, we have an appropriate visit method, and we just write code that corresponds to it. So for example, if we're visiting a not expression, well, how do we collect the sub-expression corresponding to not expression? Well, easy. We're just going to add it to our collection. For an end expression, same thing. Just add it to our collection. For or expression, same thing. Just add it to our collection. So this part the block of visit methods, this is where we focus on what do we do for each individual element. We also may need to have some kind of just global methods to get us started. So we have the identity hash set that keep track of all of the expressions that we have, right? And note that here we decided to use identity because we want to make sure that even if we have two expressions that mean the same thing twice, we do want to keep track of them and know that there's two of them. And then we have just a helper methods to get us started. So in a constructor, for example, we call traverse. We have a function to extract all expressions from an assignment, and it simply extracts the expression of an assignment, creates a new extract all expressions, and then returns that set. And we also have all expressions for a program, which traverses and does the same thing to every assignment statement in the program. Okay? But where this thing shines is that once we get used to how the visitor pattern works, we only think about what we want to do at every expression, and we don't have to worry about how we're going to get to them. We know that because we subclass post order, so we know that. And we don't need to know how do we know whether an expression is an and, an or, a not, and so on and so on. So as I said, there's a lot of moving pieces, and the easiest way to understand it is not to listen to me explain it again, but just to go and try that code and add a few print statements or go in a debugger and just get used to once how it actually executes. And once you believe that it will execute sort of how I claim it executes, then you can abstract all of that away, and you're just thinking about everything in terms of visitors. That, what do I need to do at every expression? And then somehow the right code gets executed in the right time. So the things to look at are, we have an expression visitor base class. It creates the visit methods, but doesn't actually do anything. All the visit methods are abstract. Inside every element of a hierarchy, we have an accept method. So let's look for one here. There's an accept method, and the accept method simply calls an appropriate visit function. That's it. It's not recursive. It's very simple. It just uses polymorphism to call a method with the right type. And then in our example, we have a post order expression visitor because we'll often want to visit things in a post order way that implements how expressions are traversed. And that's it. Then the visitors that we create, if they're post order, then they simply extend the post order expression visitor and focus on the visit methods. So if you haven't seen the visitor pattern before, and that's the first time you're seeing it, I would expect you all to be quite confused by this. And again, all you have to do is just try a small program, draw a diagram, and after a little time, it should make sense. Just how those pieces connect. There's nothing really magical in there. It's just a clever way to connect all the pieces using polymorphism. So let's go back to our slides. Okay. So what's the difference between visitor and interpreter? So interpreter, the big thing about it is that it's much easier to understand. It's an easier way to structure the code. The problem with it is that it's much harder to add new operations because every time you have new functionality, like for example, extract all expressions, you have to go and change everything in the hierarchy, possibly stamping on others' code. And the hardest thing is when you did a functionality and you realize that you don't need it, removing it is really hard because now it's in this global, in the common AST classes. Others may start using it, and it'll be maybe very complicated to decide, how to remove the functionality if for some reason you decided it's no longer needed. The visitor pattern gives you more flexibility. It is harder to understand because it's based on this polymorphism trick. So with separating the code, it's just a little bit harder to understand how everything is connected together. But once you do, you need to do it only once for just visitor in general. And you'll be able to understand implementations of visitors in this code and in lots of other codes. If you haven't seen a visitor before, just Google for it now, and you'll see that it's used all over the place. It's one of the most common design patterns. It's especially good because it's easy to add new operations. Every time you want to do something new with your hierarchy, it's just a new visitor. It's all one class. You keep it together. You want to add it, you add it in. You want to remove it, you remove it. The difficulty is, of course, that if you're adding a new data type to a hierarchy, that gets harder because you have to go to all the visitors and add the visit method all over the place. There's a question in chat about something, but I don't understand that question, so maybe we can take it offline. Yeah, I can't quite parse it. Okay, so interpreter, visitor. Interpreter is easier. This is usually what you start with, and as soon as your things mature enough, you switch to visitor. As this thing says it. So visitors are good. It says compilers, but it's really any data structures you have. So if you have a data structure which has this hierarchical nature, like an AST, as soon as you're pretty sure that your data structure is fixed and you're not going to be adding new elements to it all the time, you start using a visitor. If you're not sure, you're just prototyping, then you'll probably use an interpreter pattern at first and then migrate to visitor. Okay, and there will be questions like this on the final. This is so hopefully once you use the visitor pattern in the lab, that'll be easy, where we'll have to draw an object diagram and basically explain what gets called and when and how. There are questions like this in the study questions, so you should be able to see them there. Okay, so we still have a little bit of time to the last part, which is the common sub-expression elimination. Okay. So the goal here is to, given a bunch of expressions, so in our case, a bunch of assignments, like the guys here, to refactor them in such a way that common sub-expressions is computed only once. So in this case, our common sub-expression is t, which is b times c, and we want to refactor it out. So whenever we look at this expression, we find out all of its sub-expressions. We find out which ones are equal, and only use it once. Give it an intermediate variable and use it once. Now, in our case, this problem is actually quite easy. The problem gets a lot harder when we have reassignment in the language. So this is an example in here. So here, for example, it looks like we have the same computation twice, but it's not the same because C gets reassigned in the middle. And so it's important to know not just whether we have two sub-expressions which are identical, it's also important to know that whether there's some kind of things happening in between the computation of the two expressions that somehow affect them. Now, this is what we're going to be covering starting a week from now, which will be data flow analysis for a languages with assignment. This is going to be part of our optimization section. But for the F language, we don't have this problem. There are no reassignments. So all we have to do is figure out if we have expressions, whether they happen to be the same, and just use the expression once. So this is maybe a good example to look at. So if we look at this F program as an input, so we have two outputs, X and Y, and the following inputs. So if we don't remove common sub-expressions, then this thing, A or B, gets to be computed twice, once here, once here. And with common sub-expression elimination, we expect it to only be here once. So this is what we want to go. We want to go from here to here. Now, of course, so you given some of the basic code and some structure. There is a fairly long description in the lab manual of how to design this. There are many different designs that are possible. There is one that is sketched in the notes, and this is sort of sketched a little bit in the skeleton, but you don't have to use it. You can come up with your own designs, not the one that is sketched in there. There's a few that are simpler to implement that are sketched in the manual, and so you may elect to use that one rather than the one that is sort of sketched in the skeleton as an implementation. Right, and of course, these things will come into play. That's why we're covering them now. What do I want to say about this? So if you think about how to design this, yeah, no, I don't want to talk much about design. So if you have questions, ask on CampusWire. I don't want to talk much about the design because there's one way, the way I would design it, where I'll try to make it both efficient and easy to implement. But it's not necessarily the simplest way to implement if it's the first time you see this problem. I don't want to say too much to not sort of make you think one way or another. Right? Just look at this picture and think about how you would implement that. So how you would go from this to this. Okay, I think that's everything that we have for today. So if you have questions, ask them now or on CampusWire later. And I'll see you all on Monday. On Monday, on our plan is to go over the midterm. The midterm is still being marked. It doesn't look like it will be marked by Monday, but we'll try to mark it as soon as possible. If you have particular questions from the midterm that you want me to cover, say something, and I'll make sure to cover them. Otherwise, I'll pick some that I find most interesting, or I'll find from our TAs which questions people make most mistakes on, and we'll cover those. That's it. So there's a question on CampusWire that this common sub-expression elimination is somehow related to subset absorption. And yep, so some of the techniques would be similar because in a subset absorption, you're finding out that certain things are similar and then you can remove them. And here you're gonna find out that certain things are similar. And so if you already have a circuit constructed for one, then you don't need to construct the circuit for the other. You can just reuse the same circuit and add a different, and add an extra wire. Okay, that's it for today. I'll see you again on Monday.